Space is crazier than you think. Seriously. The universe isn't just a quiet, dark expanse dotted with twinkling lights. It's an active, dynamic, and often downright bizarre stage for the grandest cosmic drama imaginable. Every discovery we make seems to peel back another layer, revealing phenomena that challenge our understanding of reality itself. From the mind-bending physics governing black holes to the sheer, unimaginable scale of cosmic structures, there's a universe of wonder out there that often defies our everyday intuition. We're constantly learning, constantly being surprised, and constantly reminded of how much more there is to explore. Today, we're going on an expedition, a journey through some of the most astonishing aspects of our cosmos. Forget the basics you learned in school. We're venturing into the territory of the truly extraordinary. I've gathered some of the most fascinating, perplexing, and utterly cool tidbits that scientists have uncovered about the vast expanse beyond our world. Here are 15 mind-blowing facts about the universe you probably haven't heard, each one a testament to the universe's boundless capacity to amaze. These aren't just trivia, they are insights into the fundamental workings of everything. So, buckle up your curiosity, open your mind to the incredible, and prepare to have your cosmic perspective expanded. We're about to explore concepts that will twist your perception of space, time, and even reality itself. This journey promises to be enlightening, perhaps a little unsettling, but undoubtedly awe-inspiring. Are you ready to confront the universe in its full, bewildering glory? Let's dive in! Our universe is not static. It's in a constant state of expansion, a discovery made nearly a century ago that reshaped our understanding of cosmology. But here's the truly mind-bending part. The farther away a galaxy is, the faster it recedes from us. And for the most distant observable galaxies, this recession speed actually exceeds the speed of light. Now you might be thinking, hold on, I thought nothing could travel faster than light. And you'd be right, according to Einstein's theory of special relativity. Nothing within space can accelerate past the cosmic speed limit of approximately 299,792 kilometers per second. This fundamental constant governs the motion of all matter and energy moving through the fabric of space-time. However, the expansion of the universe is a different phenomenon altogether. It's not about galaxies rocketing through space like cosmic bullets. Instead, it's the very fabric of space-time itself that is expanding, stretching like an inflating balloon. Imagine dots drawn on the surface of that balloon. As it inflates, the dots move apart from each other, not because they are crawling across the rubber, but because the rubber itself is expanding. Similarly, distant galaxies are carried along by this cosmic expansion. There's no universal speed limit on how fast space itself can expand. The light from these distant, rapidly receding galaxies is stretched or redshifted on its long journey to us, providing evidence of this astonishing expansion. This concept, often referred to as Hubble's law, or more accurately the Hubble-Lemaire law, paints a picture of a dynamic and evolving cosmos. The rate of this expansion is characterized by the Hubble constant, though recent measurements have shown some intriguing discrepancies, hinting at new physics we've yet to uncover. The realization that space itself can stretch faster than light can traverse it opens up profound questions about the ultimate fate of the universe and the nature of the observable cosmos. It implies that there are regions of the universe whose light will never reach us, effectively beyond our cosmic horizon, forever hidden from our view due to this relentless expansion. So while an astronaut in a spaceship can't hit the hyperdrive and break the light barrier relative to their local environment, the universe as a whole plays by a grander set of rules. The expansion doesn't violate special relativity because the galaxies aren't locally breaking the speed of light. They are simply riding the wave of expanding space-time. This distinction is crucial and highlights the often counterintuitive nature of cosmic physics. It's a universe that continues to surprise us, pushing the boundaries of our comprehension with its sheer scale and the exotic laws that govern its behavior. Let's take a trip to our planetary neighbor Venus, a world often called Earth's sister planet due to its similar size and mass. However, beneath its thick, perpetual cloud cover, Venus is a place of extremes, and one of its most peculiar characteristics is its incredibly slow rotation. A day on Venus, meaning one full rotation on its axis, takes about 243 Earth days to complete. This is an astonishingly leisurely spin, especially when you compare it to Earth's brisk 24-hour rotation. Imagine a sunrise that lasts for months, followed by an equally long sunset and night. The pace of day and night on Venus is unlike anything we experience. Now consider Venus's journey around the Sun. An orbit, or a Venusian year, takes approximately 225 Earth days. If you're doing the math, you've already spotted the oddity. A single day on Venus, 243 Earth days, is longer than its entire year of 225 Earth days. This means that if you were standing on the surface of Venus, you would experience the sun rising and setting, but an entire year would pass before a single Venusian day-night cycle is complete. It's a bizarre temporal landscape that challenges our Earth-centric notions of how celestial bodies should behave, a true testament to the diverse mechanics at play in planetary formation and evolution. Adding another layer of weirdness, Venus rotates retrograde, meaning it spins in the opposite direction to most other planets in our solar system, including Earth. So on Venus, the sun would appear to rise in the west and set in the east. Why Venus has such a slow, backward rotation is still a subject of scientific debate. Theories range from colossal, ancient impacts that might have drastically altered its spin, to the complex interplay of its thick, super-rotating atmosphere with its solid body, creating tidal forces that gradually slowed its rotation over billions of years. The atmospheric dynamics on Venus are themselves extreme, with winds at high altitudes whipping around the planet much faster than its surface rotation. This peculiar relationship between its day and year, combined with its retrograde rotation and runaway greenhouse effect, leading to surface temperatures hot enough to melt lead, makes Venus a truly alien world. It serves as a stark reminder that even within our own solar system, planetary conditions can vary dramatically. Understanding these differences helps us appreciate the delicate balance of factors that make Earth habitable and provides crucial context for our search for life elsewhere in the universe. Venus is a cosmic laboratory for studying planetary extremes, and its slow day is just one of its many fascinating enigmas. Prepare yourself for a truly infernal weather report from an exoplanet some 63 light-years away, a gas giant named HD 189733b. This planet, slightly larger than Jupiter, orbits incredibly close to its parent star, completing a full revolution in just over 2 Earth days. This proximity results in scorching temperatures on its day side, estimated to be around 1,000 degrees Celsius or about 1,800 degrees Fahrenheit. But it's not just the heat that makes this world terrifyingly exotic. It's the composition of its atmosphere and its extreme weather patterns. Observations have revealed that HD 189733b has a deep blue hue, reminiscent of Earth, but this color comes from a far more sinister source than our oceans. Scientists believe the blue color is due to silicate particles in its atmosphere, essentially tiny grains of glass. Now combine these glass particles with the planet's ferocious atmospheric conditions. The temperature difference between its star-facing side and its night side drives incredibly powerful winds, estimated to blow at speeds of up to 8,700 kilometers per hour, or over 5,400 miles per hour. That's more than 7 times the speed of sound. These are not gentle breezes. These are planet-circling gales of unimaginable ferocity, capable of whipping those silicate particles around at incredible velocities. The result? It's believed to rain glass on HD 189733b. And not just any rain, but sideways rain, driven by those hypersonic winds. Imagine a perpetual storm where molten glass particles condense in the cooler parts of the atmosphere and are then blasted horizontally through the air at thousands of miles per hour. This isn't the kind of weather you'd want to experience without some serious futuristic protection. The sheer violence of this environment is difficult to comprehend, painting a picture of a world constantly ravaged by a tempest of superheated, razor-sharp projectiles. Discoveries like this highlight the incredible diversity of exoplanets. While we search for Earth-like worlds, the universe presents us with countless examples of planets that are wildly different from anything in our solar system. HD 189733b, with its azure allure hiding a nightmare of glass storms, serves as a potent reminder that exotic doesn't even begin to cover the range of planetary environments out there. It pushes the boundaries of what we thought possible for weather systems and atmospheric composition, offering a glimpse into the truly extreme conditions that can exist on other worlds. Let's delve into one of the most extreme and fascinating objects the universe has to offer, the neutron star. These celestial bodies are the collapsed cores of massive stars. Stars that were once many times the mass of our sun, which have exploded as supernovae. What's left behind after such a cataclysmic event is an object typically only about 20 kilometers or 12 miles in diameter, roughly the size of a city. Yet, crammed into this incredibly small volume is a mass that can be up to twice that of our sun. The density involved is almost beyond human comprehension. To try and grasp this, imagine taking a teaspoonful of neutron star material. That tiny amount, no bigger than a sugar cube, would weigh an astonishing billion tons on Earth. That's like squeezing Mount Everest, or perhaps several mountains, into a volume you could hold in your hand if you could somehow survive the experience, which, spoiler alert, you couldn't. The gravitational forces at the surface of a neutron star are immense, billions of times stronger than Earth's gravity. If you were to drop an object from a height of 1 meter onto a neutron star, it would hit the surface at a speed of several million miles per hour. The reason for this incredible density lies in the way neutron stars are formed. During the supernova explosion, the core of the star collapses under its own immense gravity. The pressure is so intense that it overcomes the forces that keep atomic nuclei apart. Protons and electrons are crushed together to form neutrons, hence the name neutron star. The entire star becomes a giant nucleus, packed almost entirely with neutrons, squished together as tightly as the laws of physics allow. This state of matter, known as neutronium, is one of the densest forms of matter known to exist in the universe. Neutron stars also often spin incredibly rapidly, some rotating hundreds of times per second, a consequence of the conservation of angular momentum from their much larger parent star. Many also possess incredibly strong magnetic fields, trillions of times stronger than Earth's. When these spinning, magnetized neutron stars emit beams of radiation from their poles, and these beams happen to sweep past Earth, we observe them as pulsars, cosmic lighthouses blinking with astonishing regularity. Neutron stars are not just dense, they are extreme laboratories for physics, pushing our understanding of matter, gravity, and magnetism to their very limits. We often think of our sun as a large and powerful star, and in many ways it is. It's the center of our solar system, the source of all our light and heat, and it certainly dwarfs our tiny Earth. However, on a galactic scale, our sun is rather average. There are stars out there that make our sun look like a mere speck of dust. One such behemoth is Scuti, a red hypergiant star located in the constellation Scutum, about 9,500 light-years away from us. It currently holds the title as one of the largest known stars by radius. To put its size into perspective, if Scuti were placed at the center of our solar system, its surface would extend out past the orbit of Jupiter, and possibly even close to Saturn. That means it would engulf Mercury and Venus, Earth and Mars, and the asteroid belt entirely. The volume of Scuti is estimated to be so immense that you could fit roughly 5 billion suns inside it. Let that sink in. 5 billion stars the size of our own sun could comfortably nestle within this single colossal star. It's a scale that almost defies visualization, a true titan of the cosmos. Scuti is not just large, it's also incredibly luminous, shining with a brightness hundreds of thousands of times greater than our sun. However, despite its immense size and luminosity, it's not visible to the naked eye from Earth because it's quite distant and much of its light is obscured by interstellar dust. As a red hypergiant, Scuti is in a late stage of its stellar evolution. These stars are characterized by their enormous, puffed-up outer layers and relatively cooler surface temperatures compared to stars like our sun, which gives them their reddish hue. They are also highly unstable and lose mass at a prodigious rate through strong stellar winds. Stars like Scuti don't live very long, at least not in cosmic terms. Their immense mass means they burn through their nuclear fuel incredibly quickly. It's expected that UI Scuti will eventually explode as a spectacular supernova, scattering its enriched elements back into the interstellar medium, which will then contribute to the formation of new stars and planets. Studying these stellar giants helps us understand the life cycle of the most massive stars in the universe, their impact on their galactic environments, and the ultimate fate of matter in the cosmos. They are truly awe-inspiring reminders of the sheer scale and diversity of celestial objects. Let's journey inward from Earth towards the heart of our solar system, to the smallest and innermost planet, Mercury. This rocky world, scorched by its proximity to the Sun, experiences a year that is remarkably short compared to our own. While Earth takes approximately 365 days to complete one orbit around the Sun, Mercury zips around our star in just about 88 Earth days. This means that if you were to celebrate your birthday on Mercury, you'd be having a party roughly every 3 Earth months. 4 Mercurian years would pass in the time it takes for Earth to complete just one. This rapid orbital period is a direct consequence of Kepler's laws of planetary motion and Newton's law of universal gravitation. Mercury is the closest planet to the Sun, at an average distance of only about 58 million kilometers or 36 million miles. The closer a planet is to its star, the stronger the gravitational pull it experiences from that star. To avoid being pulled into the Sun, the planet must maintain a higher orbital velocity. Mercury, therefore, travels through space at an impressive average speed of nearly 48 kilometers per second, or about 107,000 miles per hour, making it the fastest orbiting planet in our solar system. Life on Mercury, if it could exist, would be a dizzying affair of rapid seasons and frequent New Year celebrations. However, Mercury's swift year is contrasted by its very slow rotation on its axis. It takes Mercury about 59 Earth days to complete one rotation. This leads to a peculiar 3-to-2 spin-orbit resonance, meaning it rotates 3 times on its axis for every 2 orbits it completes around the Sun. This complex dance results in extremely long solar days on Mercury. From one sunrise to the next takes about 176 Earth days, which is exactly 2 Mercurian years. So while a year is short, a full day-night cycle is incredibly long. The environment on Mercury is also one of extremes. With virtually no atmosphere to trap heat or distribute it around the planet, the sunlit side can reach temperatures of up to 430 degrees Celsius, or 800 degrees Fahrenheit, hot enough to melt tin and lead. Conversely, on the night side, temperatures can plummet to a frigid minus 180 degrees Celsius, or minus 290 degrees Fahrenheit. This stark contrast, combined with its rapid orbit and slow rotation, makes Mercury a fascinating world for studying planetary dynamics and the harsh conditions that can exist so close to a star. Its swift journey around the Sun is a constant reminder of the powerful gravitational forces that sculpt our solar system. Venturing far beyond our solar system, towards the heart of our Milky Way galaxy, we encounter a truly curious celestial object, a giant molecular cloud known as Sagittarius B2. This colossal cloud of gas and dust, located about 26,000 light-years from Earth near the galactic center, is one of the largest and densest in our galaxy. It's a stellar nursery, a place where new stars are actively being born. But what makes Sagittarius B2 particularly intriguing for us today isn't just its star-forming capabilities. It's the surprising array of complex organic molecules that astronomers have detected within it, including some that might tickle your taste buds, or at least your sense of smell. Among the many chemicals identified in Sagittarius B2 is a molecule called ethyl format. Now, why is this interesting? Well, ethyl format is an ester, and on Earth it's known for contributing to the characteristic flavor of raspberries and, amusingly, the smell of rum. Yes, you heard that right. There's a giant cloud near the center of our galaxy that, if you could somehow get a whiff of it, which of course you can't, due to the vacuum of space and extreme conditions, might remind you of a cosmic cocktail or a giant raspberry patch. It's a delightful and whimsical discovery that underscores the complex chemistry occurring in the universe. Of course, Sagittarius B2 doesn't actually contain barrels of rum or fields of raspberries. The presence of ethyl formate, along with other organic molecules like ethanol and vinyl alcohol, is a result of complex chemical reactions occurring on the surfaces of dust grains within the cold, dense cloud. These molecules form as atoms and simpler molecules collide and combine over vast timescales, often catalyzed by ultraviolet radiation from nearby stars. The detection of such complex organic molecules in interstellar space is profoundly important because these are the very building blocks from which life, as we know it, could potentially arise. The study of astrochemistry, the chemistry of the cosmos, reveals that the universe is a surprisingly flavorful and fragrant place, at least in terms of its molecular constituents. These vast clouds are like cosmic chemical factories, churning out a rich tapestry of compounds. While Sagittarius B2's raspberry rum aroma is a fun fact, it points to a deeper truth. The ingredients for life are not unique to Earth. They are widespread throughout the galaxy, embedded in the very clouds from which stars and planetary systems form. It makes you wonder what other flavors are waiting to be discovered in the cosmic kitchen. We often marvel at the densely packed clusters of galaxies, the brilliant nebulae, and the sheer abundance of stars in the night sky. The universe, as we typically picture it, is full of stuff. However, the cosmos is also home to regions of astonishing emptiness, vast cosmic deserts known as voids. One of the most famous and largest of these is the Bootes Void, sometimes called the Great Nothing or the Super Void. Discovered in 1981, this colossal region of space presents a stark contrast to the bustling galactic neighborhoods we're more familiar with. The Bootes Void is roughly spherical in shape and has a diameter of nearly 330 million light-years. To put that into perspective, our own Milky Way galaxy is about 100,000 light-years across. You could fit thousands of Milky Way-sized galaxies end-to-end across the Bootes Void. If our galaxy were situated in the center of this void, we wouldn't have known of the existence of other galaxies until the 1960s, when telescopes became powerful enough to detect the faint, distant smudges of light from its far-off edges. It's a region so sparsely populated that it challenges our intuitive sense of cosmic structure. Initially, astronomers could only identify a handful of galaxies within this immense volume, leading to its nickname, the Great Nothing. While further surveys have since found a few dozen more galaxies scattered throughout the Bootes Void, it's still remarkably underdense compared to an average region of the universe. If the universe were a sponge, the voids would be the large holes, and the filaments and clusters of galaxies would be the sponge material itself. These voids are not entirely empty. They do contain some matter, including dark matter and a very tenuous distribution of hydrogen gas, but they are conspicuously lacking in luminous galaxies. The existence of such enormous voids is actually predicted by models of cosmic structure formation. According to these models, the universe evolved from a nearly uniform state after the Big Bang. Tiny quantum fluctuations in the early universe were amplified by gravity over billions of years, causing matter to clump together in some regions, forming galaxies, clusters, and superclusters along filaments, and to move away from other regions, leaving behind these vast empty spaces. The Bootes Void, therefore, is not an anomaly but rather an extreme example of the large-scale structure of the universe, a testament to the relentless work of gravity sculpting the cosmic web over eons. Black holes are often portrayed as eternal cosmic vacuum cleaners, relentlessly gobbling up anything that ventures too close, and from which nothing, not even light, can escape once past the event horizon. For a long time, this was the prevailing view, that black holes only grow, never shrink. However, in 1974, the brilliant physicist Stephen Hawking introduced a revolutionary idea that turned this notion on its head. He proposed that black holes are not entirely black but can in fact slowly lose mass and energy over incredibly long timescales through a process now known as Hawking radiation. Hawking's theory ingeniously combines principles from general relativity, which describes gravity and black holes, and quantum mechanics, which governs the behavior of particles on very small scales. According to quantum field theory, empty space is not truly empty, but is a seething cauldron of virtual particle-antiparticle pairs that constantly pop into existence, and then annihilate each other almost instantaneously. Near the event horizon of a black hole, the immense gravitational forces can sometimes pull these virtual pairs apart before they have a chance to annihilate. One particle might fall into the black hole, while the other escapes into space. To an outside observer, it would appear as if the black hole is emitting radiation. The particle that falls into the black hole has negative energy relative to the outside universe, which effectively reduces the mass of the black hole. The escaping particle carries away positive energy, appearing as thermal radiation. This means that, very, very slowly, black holes can evaporate. The temperature of this radiation is inversely proportional to the black hole's mass. Smaller black holes are hotter and evaporate faster, while supermassive black holes are incredibly cold and take an unimaginably long time to disappear. For a solar mass black hole, the evaporation time is vastly longer than the current age of the universe, something like 10 to the 67th power years. For supermassive black holes found at the centers of galaxies, this time scale is even more astronomical. So we're not going to see any black holes vanishing before our eyes anytime soon. However, Hawking radiation is a profound theoretical concept. It suggests a deep connection between gravity, thermodynamics, and quantum mechanics, and it's a crucial piece in the puzzle of understanding the ultimate fate of black holes and the universe itself. It implies that even the most formidable objects in the cosmos are not truly eternal. So, you know that famous line from science fiction in space? No one can hear you scream? Well, that's actually pretty accurate, since sound needs something like air or water to travel through. Out in the vastness of space, there's just not enough particles for your voice to make any waves. That's why all those loud spaceship battles in movies are just Hollywood magic. But here's the twist. Space isn't totally silent. Sound waves can travel through plasma, which is this super hot state of matter where atoms are stripped into ions and free electrons. Even though space looks empty, it's filled with really thin plasma, like the solar wind or the stuff between galaxies. These plasmas can carry waves, kind of like sound waves called plasma waves or magnetosonic waves. They're not sounds you'd hear with your ears, since their frequencies are way outside what we can pick up. But scientists have instruments on spacecraft that detect the waves and convert the data into sounds we can hear. NASA has released sounds from Jupiter's magnetosphere, or the plasma around Earth. You can't yell to your buddy across a vacuum, but the universe isn't totally silent. It's got its own symphony of plasma waves, cosmic music that plays on a huge scale. These waves carry energy and information, affecting the solar wind's interaction with planets, the heating of the sun's corona, and what happens around black holes. What seems like empty space is actually full of incredible activity. When you think about the coldest spots in the universe, you probably imagine those lonely, dark spaces between galaxies, way out away from any stars. The background temperature out there, set by the cosmic microwave background, the leftover glow from the Big Bang, is about 2.7 Kelvin, which is like minus 270 degrees Celsius. That's just a hair above absolute zero, where atoms basically stop moving. For a long time, people thought that was as cold as it could get, at least naturally. But get this, the coldest place in the universe isn't out in space at all. It's actually been created right here on Earth in physics labs. Scientists, in their quest to figure out how matter and quantum mechanics work, have managed to cool stuff down to temperatures way, way colder than the cosmic microwave background. We're talking fractions of a degree, sometimes billionths or even trillionths of a degree, above absolute zero. How do they pull that off? Well, they use things like laser cooling, where lasers are tuned just right to slow down atoms and make them colder, and evaporative cooling, which is actually a bit like how sweating cools you off, by removing the hottest atoms from a group and leaving the rest colder. By combining these tricks, physicists can make clouds of atoms so cold that they form something called a Bose-Einstein condensate. That's a state where the atoms kind of lose their individual identities and act as one big superatom. Studying these lets scientists see quantum effects on a larger scale, opening up a whole new world of physics. Some of these super cold experiments even happen on the International Space Station in the Cold Atom Lab, where microgravity helps them observe things for longer. So while space is definitely freezing, humans have actually made even colder places here on Earth, all in the name of science. Whenever we look up at the stars, or even use the most powerful telescopes, we're seeing just the observable universe. That's the part of the cosmos where light has had enough time to reach us since the universe began, about 13.8 billion years ago. Because light only travels so fast, there's a limit to how far we can see. This is called the cosmic horizon. Right now, that sphere is about 93 billion light-years across, thanks to the way space itself expands as light travels. It's a mind-blowing amount of space, packed with hundreds of billions, maybe even trillions of galaxies, each with its own billions or trillions of stars. But here's where it gets really wild. The observable universe is almost certainly just a tiny sliver of the whole universe. Based on what we know from cosmology and the way the cosmic microwave background looks, it seems like the universe is way bigger than what we can see, maybe even infinite. Imagine you're on a ship in the middle of the ocean. You can only see as far as the horizon, but you know the ocean goes way beyond that. Our cosmic horizon is kind of like that. It's not a wall or an edge, just the farthest distance light has traveled to us so far. There could be countless galaxies, stars, and maybe even other observable universes out there that we just can't see yet, because their light hasn't reached us. The laws of physics should be the same out there, but we'll never be able to check directly. So it really changes how we think about our place in the universe. We're not at the center of everything, just peering at a tiny patch of a much, much bigger reality. It's kind of humbling to realize that, as huge as the universe looks to us, it's probably just a tiny speck in something even more immense. We've all stood on a beach or in a desert and marveled at the seemingly countless grains of sand. Trying to count them individually is an exercise in futility. Their sheer number feels overwhelming, practically infinite from our perspective. It's a common analogy for something incredibly numerous. Yet, when we turn our gaze to the heavens, the number of stars in the universe likely dwarfs even the total number of sand grains on all the beaches and deserts of Earth. This comparison really tries to give us a sense of the true immensity of the cosmos. Estimating the number of stars in the universe is a pretty complex task. We start by estimating the number of stars in our own Milky Way galaxy. Current figures range from 100 billion to 400 billion stars. Then we estimate the number of galaxies in the observable universe. Observations from the Hubble Space Telescope and other instruments suggest there are at least 200 billion galaxies, and some newer estimates push this number as high as 2 trillion galaxies. If we take a conservative average of 100 billion stars per galaxy and multiply that by 2 trillion galaxies, we arrive at a staggering number, 200 sextillion stars. That's a 2 followed by 23 zeros. Now, how does this compare to grains of sand? Estimates for the total number of sand grains on Earth vary, but a commonly cited figure is around 7.5 sextillion. So even with conservative estimates for stars and generous estimates for sand, the stars appear to win out, potentially by a significant margin. There could be 10 or even 100 times more stars in the observable universe than there are grains of sand on our entire planet. It's a comparison that really stretches the limits of our imagination. This isn't just an idle numbers game. It underscores the vastness of the cosmic stage and the potential for discovery. Each of those stars could potentially host its own system of planets. If even a tiny fraction of those planets are habitable, the number of possible abodes for life in the universe becomes, well, astronomically large. Thinking about this cosmic sandstorm of stars helps us appreciate our own smallness, but also the incredible richness and potential of the universe we inhabit. It's a scale that invites humility and inspires an unceasing curiosity to explore and understand. Now we venture into one of the more speculative yet deeply intriguing ideas in modern theoretical physics, the holographic principle, which suggests that our universe, with its 3 spatial dimensions, might actually be a kind of hologram. This doesn't mean we're living in a computer simulation run by advanced aliens, though that's a separate, fun thought experiment. Rather, it proposes that all the information contained within a volume of space, like our universe, can be described by a theory that lives on the boundary of that space, a surface with one fewer dimension. The idea originated from studies of black hole thermodynamics. Jacob Bekenstein and Stephen Hawking discovered that the entropy of a black hole, basically a measure of its information content, is proportional to the area of its event horizon, its two-dimensional surface, not its three-dimensional volume. This was a surprising result because usually information capacity scales with volume. It suggested that the maximum amount of information you can pack into a region of space is determined by its surface area, as if the three-dimensional reality were somehow encoded on a two-dimensional screen. Physicist Gerard T. Hooft later formalized this into the holographic principle, and Juan Maldacena provided a concrete mathematical example with the ADS-CFT correspondence, which relates a theory of gravity in a three-dimensional bulk space to a quantum field theory on its two-dimensional boundary. While this is highly technical and specific, it provides strong theoretical evidence that such a holographic relationship might be a fundamental feature of reality. If this principle applies to our universe, it means our perceived three-dimensional existence could be an emergent phenomenon, a projection from a lower-dimensional reality. It's important to stress that this is still a theoretical concept, and there's no direct experimental proof that our universe is a hologram. However, some researchers are looking for potential observational signatures, such as specific patterns or noise in the cosmic microwave background that might betray a holographic origin. Whether true or not, the holographic principle forces us to question our fundamental assumptions about space, time, and information. It suggests that reality might be far stranger and more interconnected than we can easily imagine, with deep links between gravity and quantum mechanics that we are only just beginning to explore. One last fact that'll blow your mind, and it comes straight from Einstein's theory of general relativity. Time itself is not constant throughout the universe. It's malleable, stretchable, and can be warped by gravity. The stronger the gravitational field, the slower time passes relative to a region with weaker gravity. This phenomenon is known as gravitational time dilation, and it has actually been experimentally verified. For example, clocks on GPS satellites, which experience slightly weaker gravity than clocks on Earth's surface, run a tiny bit faster and need to be constantly corrected to maintain accuracy. Now, let's take this to an extreme. Imagine a black hole, an object with such immense mass and gravity that it creates a deep well in the fabric of space-time. As you get closer and closer to the event horizon of a black hole, the gravitational pull becomes incredibly strong, and consequently, time slows down dramatically for you relative to an observer far away. If you could hover just outside the event horizon, a feat requiring unimaginable technology to avoid being pulled in hours, for you could equate to years, centuries, or even millennia passing for the rest of the universe. This leads to a fascinating, albeit highly impractical form of theoretical time travel into the future. If you were to take a spaceship orbit a supermassive black hole for a while from your perspective and then return to Earth, you would find that much more time had passed on Earth than for you. You would have effectively journeyed into Earth's future. This isn't science fiction in the sense of violating known laws of physics. It's a direct consequence of how gravity affects time, according to our best current theories. The challenge, of course, lies in surviving the extreme tidal forces, and having the propulsion to maneuver near such an object while traveling back in time is fraught with paradoxes and likely impossible under known physics. Though wormholes offer speculative loopholes, one-way trips to the future via time dilation are theoretically sound. This effect isn't limited to black holes. Any massive object warps space-time and affects time's flow, but black holes represent the most extreme examples. It's a profound realization that our experience of time is not absolute, but depends on our gravitational environment and our motion through space. The universe, it seems, has its own built-in mechanisms for temporal distortion, reminding us once again of its incredible and often counterintuitive nature. And there you have it, 15 glimpses into the astonishing, bewildering, and utterly captivating nature of our universe. From the mind-bending expansion of space itself to the bizarre weather on distant exoplanets, the cosmic rum cloud, and the theoretical possibility of time travel near black holes, it's clear that reality is far grander and stranger than we often imagine. Each of these facts is a testament to the power of scientific inquiry and our innate human desire to understand our place in the cosmos. The universe is under no obligation to make sense to us, yet with every new discovery, we piece together a more complete and often more wondrous picture. The journey of cosmic discovery is far from over. There are still countless mysteries waiting to be unraveled, from the nature of dark matter and dark energy to the ultimate fate of the universe and the question of whether we are alone. The more we learn, the more we realize how much more there is to know. It's a humbling and exhilarating prospect. These facts aren't just trivia, they are invitations to ponder, to question, and to marvel at the sheer scale and complexity of existence. So what do you think? Which fact shocked you the most? Or do you think we're alone in the universe? Let us know below. Your thoughts and questions fuel the conversation and help us all explore these cosmic wonders together. Thank you for joining me on this journey. Until next time, keep looking up and never stop questioning.